Hello and welcome in, everyone. I am your host, Code Wonderland, and today we are playing Comet 64. Now, this is a new game to you, to me, I don't know if it's new to you, but it's new to me, and I'm pretty excited to play it. I've been looking for other games to try out on this channel, because I kind of wanted this YouTube channel as opposed to my Twitch to be like a more like coding focused kind of gaming. A little bit of like extra coding stuff, but mostly coding gaming. And Comet 64 popped up as something that really differs from a lot of your conventional programming games. I feel like most of your programming games are like either hacking or competing with bots against each other. This is a series of puzzles. So we're going to see how this goes. So I don't really know what I'm doing. I know that the general like guide or how to of this is that we have this Comet 64 as kind of similar to a very famous Commodore 64, and we were given really nothing on how to use it other than this user manual and then some other things here. And so it's up to us to figure out how to use it. So let's start with the user manual. Print hello world. Okay, first things first, relax. And thank you for purchasing the Comet 64 home computer. All this talking to computers business might seem crazy or daunting at first. The machine has a complex and foreign language after all, but there is something magic about it. After a while, it becomes like second nature. You become fluent, and then it's like you are talking to an old friend. It's like you were a magician. In the following pages, I tried and documented its operations as well as I knew how to. So welcome aboard and see you on the other side. Good luck, Otari. So we have a few categories here. We're not even getting into these others yet. I don't know what these are for. I'm guessing these are like puzzles, probably. But here's our documentation. So we have the welcome, we have interface, syntax, code, logic, extras, and reference. I'm guessing we should probably go through these in order. So from the top, press tab to toggle the ports and register panels on and off. So tab. This is for the programming interface. Got it. Um, right, because we have ports and interfaces. Cool. Or ports and registers. It's just interesting because I've used registers in assembly. I've used ports with web development and other kinds of like server development. Interesting that we have them both here in one singular panel. I like that, but I'm curious to see how that works. At the bottom of the screen, there are input and output ports. They are folded. Pressing tab or clicking on one of them will unfold them. You can think of them as conveyor belts. The computer can read values from the input, process them, and finally write them to the output in rapid succession. Your task will be to write the instructions to tell the computer what to do step by step. Okay. So, let's see. Those are the ports. Interesting. I would have thought those were the registers. Um, but I guess they're just different names for different things. Um, Alright, so then we have buttons, stop, stops, pause, pauses. Stops, and rewinds. Well, I guess that makes sense. Step executes one line of the instructions, just like it would in any kind of debug state. Play plays it. Fast forward. Oh, I see. So play is playing it at visual speed. Fast forward run is playing it at like normal speed. When the last instruction is executed, the program will jump to line 1 and continue processing. So it'll just keep looping. Program will stop either by outputting the required number of items or hitting an error. Error messages will help identify the line number at which the error occurred as well as the cause of the problem. So say we had a task to produce 3 apples. If I wrote a script that produced 1 apple, I could just run it and it would run 3 times in a row and then finish. Makes sense. Or if an error hits, it'll stop. Syntax. Register panels contain 5 types of registers, which are reg, which can store float value, so decimal point value, integer, number without a decimal. There's more to it, but in this instance, that's probably all that it means. Boolean, true or false, string, series of characters, character, a single character. Boolean is read only. Huh. Okay. Good to know. Oh, and these are all the descriptions of what these are. If you need examples for such things, integer does include negatives here as well. Most integers would in a programming sense. There's probably just a limit to how far up you can go with that. Um, but we'll see. I mean, there is, but we'll see if we ever come close to it. Well, writing a decimal value to int will drop its decimal part. Writing an integer to reg will. I see, I see. So you're losing precision if you write a decimal to an int, but you're not doing so if you write an integer to a decimal or reg. Um, but you can do that. They're not going to stop you. You can still write an integer to a reg. You can still write a reg to an int. Just note that it'll cut off those decimal points if you were taking a floating point value and putting it into an integer spot. So now we have operators, pretty straightforward: equals, addition, subtraction, multiplication, division. All right, so type of operands, we have registers, which includes your basic reg, which is a float. I don't like that nomenclature, but of course this is supposed to be the 80s, so I guess that's fine. For reference, the Commodore 64 came out. What year did it come out? Was it 1984? When did the Commodore 64 launch? 1982, August of 1982. And the documentation was about like this. I feel like this is probably pretty accurate. So ports are input and output, and constants. Constants are just constants. Okay. Those are just, you throw in a 15 or a 1.4, whatever. Whatever an elf is. That looks like an assembly function, but we'll get to that. Okay, so a few examples below. We got that. Reg equals 1.4, int equals 124, string equals paper, car equals e, output equals 53. And output is going to be a register, or a port. That's right, because you have your ports input and output. I thought that those were a series of values. Oh, but they would because it's a data stream. Got it. Got it. We'll get to that. All right. Reading from registers. Okay, because that's writing to. This is reading from. Reg equals int. Output equals reg. Int equals input. Output equals input. Great. You can read what those do there. Arithmetic operators. Sounds good. You notice when we're reading from registers, we're still writing to other registers. Because that is the easiest way, I would assume. I mean, where else are you going to put it realistically? You don't have variables like other languages. This is more like assembly. You have registers that you can put data into. Although, technically, depending on the syntax, I think actually most modern syntax of assembly, you do technically have variables, but it's different than what you would expect. Alright, in the upper right corner you can see the switch box. Switch can store a value from any register, but can not be directly written or read. Instead, it switches the value of a register with the value that's stored in switch. Interesting. That's weird. So it's just your RAM, effectively. It can technically hold anything, and it'll convert the things, I'm assuming, to what they should be. So like a 1 would be a true. A true. I don't know what that would turn into. Maybe the string true? Maybe. I don't know. Because the empty string would be false. We'll get to that. We can do some tests. Labels can be used to mark a place in the program in order to jump to that line later. Any word can be a label as long as they're the only instruction at that line, such as note. Oh, such as label, start, and negative begin here. Technically, this would be considered a label as well, but then you got other stuff after it, so I don't know. I've never tried to put information after a label that's not in a comment, so I don't know. I mean, that would have to break things. It's just words. So yeah. Uh, why am I debating if the note could be technically a label? Note could be a label. Everything after it couldn't be. Um, Jumps. That jumps to a label, so you can say jump to Dave if you had a Dave label. You could say jump if true, Dave if the bool is true. Jump if false, Dave if the bool is false. Wait, if false? Like I get that in a if you do if false, it just wouldn't run though. So what are we checking to see is true or false? God, I need to brush up on my assembly because I feel like there should be another variable here. We'll see in a second. I'm sure there'll be more examples. All right. We can check to see if things equal things. Uh, Checking something sets bool true or false accordingly. Oh, that's right, the bool register. So we assign to the bool register, and then we check if true, if false on the bool register itself. Or is it called a register? Let me not get confused with the names for things. Yes, it's called a register. Yeah, yeah, yeah. So ports, what that really represents then, I mean, technically it's kind of like registers, but it's more like memory addresses. Port was just a term that they used for it. Alright. Did we already read all this? We did. Advanced operands. I would like to mention that there are a few more advanced operands as well as some extras that might be a little obscure. Int equals car converts number to letter. A equals 1, B equals 2, F equals 6. Got it. Car equals int converts, back and forth. Int equals string dot length. Uh, yep. Car equals, you can index a string, got it. String 2 equals car, so you can reverse index or index assign. You can use int as the index on that string for assignment. You can do interesting. You can also use float as well, and I guess because you can use reg as an int, it just cuts off the decimal, so it doesn't matter. Cool. You can do plus plus minus minuses on int and reg to add or subtract one. Return returns the previous jump instruction. Comment is a comment. Not or exclamation is a not. A breakpoint pausing the act. Oh wait, any line with a exclamation mark will be used as a breakpoint, pausing the execution after that line. Oh, so it's not the not symbol. It is the breakpoint symbol because we're using assembly, so we need to use physical breakpoints. Got it. In modern code, you can usually just in your editor, in a lot of languages, just click right next to the line, and you could add a little dot in a lot of them to mark a breakpoint. But in assembly, that is not the case. I remember in college, I had to use a secondary program to monitor the output of the assembly as it was running on my computer and then debug it from there. I had to know a secondary language on top of I mean, it wasn't really a language, but it felt like learning a whole new language, learning how to use that debugger tool, I swear. Um, then we've got binary. I mean, yeah, I could explain binary, but I don't think that you're here for that. Then we have our references. Beautiful. Beautiful, beautiful, beautiful. And these are just like all of the different instruction lists that we have. That's it. So, and what is this? Oh, I can print these as a PDF. I like that. Hold on. Is my little printer connected? I'd print that. What happened to my cord for my printer? I'll have to figure that out later. Alright. So, launch discount. Query. Read the values from input and write them to output after a discount of 20%. Example. Input 100, 20, 45. Output 80, 16, 36. And that's why it's important that it can be run multiple times. Got it. Wait, what? Why did they do this? Oh, I see. Because they did times 20 instead of times 80. Got it. So this is pretty straightforward. They wrote the program for us. Int equals input, so we're assigning the input to int. Reg equals input, or int times, or divided by 100. Reg equals reg times 80. And output equals reg. So we can run that. And boom, we solved our first puzzle. Look at that. Straightforward. Number of lines, challenge lines. Ah. Okay, okay. Got it. So let me just, let me play with this for a second. So, realistically, we can just do output equals input times 0.8, right? Get rid of all these extra lines. We don't need that. So we just do this in one line, one function, I would assume. Use registers for arithmetic operations. Got it. Reg equals input times 0.8. Output equals reg. Run that. Need a semicolon. Got it. There we go. And there we go. We beat the optimization report. Love to see it. Return. Why so negative? Alright, input contains negative numbers only. Remove their negativity and output them. Example, input equals negatives, output equals positive. And it's only negative numbers. We know that that's the case the entire time. So let's just do int equals input. Output equals int times -1. Oh, I keep forgetting that semicolon. Too many operands. Oh, yep, I'm right. Or I was wrong. I can only use arithmetic when assigning to a register. So I take the input, I multiply it by -1 when assigning it to int, and then I assign int to output. Bada bing, bada boom, another test passed, and we met the optimization. Return. BMI Guest. Read the weight in kilograms, followed by the height in meters, values from the input, and calculate the BMI. The formula is weight divided by height squared. So, let's write this out long form first, and just pseudocode to get this correct. That's normally how I would go about this. So, we have, let's see, is the weight a red? I just realized. Are both of those reg, or are they? I'm not sure. That's a good question. So let's do reg equals input. So we pull the weight. And let's just get weight in kilograms from input. Then we move weight to switch. And let's pull up. Oh, I forgot about that. That's not what I meant to do, but I like that. Let's pull up this. So I just press switch reg or switch whatever and it works. So switch reg. And then let's see. The formula is weight divided by height squared. So I want to pull the height. So get height in meters from input. And so we get reg equals input again. And then we can actually do reg equals input. No, we can't. We need to multiply it by itself. Can I just do reg equals reg times reg? Square the height. And then how do I get back the value from switch? Let's look at this user manual again for a second. So we can assign things to output, but that's not really what we want to do. I can use reg in this kind of a setting, or I can use it to assign itself. That's fine. No. I was going to say, if the value that needed to be squared was what we got first, then it would be a lot easier, because then we could take the height, we could square it, we could put it into the, or I guess we could just then directly use input in a formula with it. Now I'm curious, what if in one line, if I call input twice, is it the same value or is it the two values? So well, I guess that doesn't really matter. No, it doesn't. Let's just run this slowly for a second. So let's play for a second. Oh, slow. So stop this for a second. We have reg equals input, and let's look at reg. Oh, it hasn't assigned yet, so step reg equals 118. So weight is not a float. That makes this so much easier. So that's there. Reg equals input. That is in fact a decimal point value. So, all right, let's stop all of this then. Let's just make int equal input. Let's get rid of these lines. Then we do reg equals input. Can I do that in one line? Maybe. Real quick though, let's just go ahead and output. Actually, hold on. Divide weight by height squared. So reg equals weight is int divided by reg, because we've already squared reg, and then output BMI. Output equals reg. So I think this works. We might be able to do it in one less line. I mean, we could definitely do this in one less line. Maybe two less lines. Let's just do it like this first, though. Let's just run it. We passed. What's the optimal? Oh. Did we already hit the optimal? Well, dang. I mean, give me a second. Let me try something. int divided by reg times reg. Can I do that? No, okay. Oh, wait, what? Put this back here. I just want to leave it complete, you know? Okay. Turn from there. Alright, ignore the input for now and output all the numbers from 1 to 100. So let's look at the user manual for a second. We use checks here. So 1 to 100. Int equals 1. Check int less than 101. And then let's see. Jump if false. End. And then we just put end at the end. Return. And actually, I don't want it to return. That's just the end. Okay. So jump if false, end. And then let's see, add. We're going to call this increment. So increment. Do we use indentation after labels? I don't think we do, but I'd like to look at an example. Yeah, I'm guessing not. All right, so increment is, and we can actually start this at 0 because we'll increment and then output int plus plus. Let's see. We'll call this emit. I don't even know if we need the extra label. Output equals int. And then I don't know if I can do multi-line labels. Can I do multi-line labels? How does that work? Oh yeah, I just use underscore. Check value. There we go. So, and I'm gonna adjust some of the spacing on this in a second, but for now, well, I guess I'll do, well, I can't do 2 spaces. That's annoying. Alright. So, where were we at? Increment, int, output there. Check. No, actually, we're fine. Then we just do jump. Check value. Right? I think so. So int equals 0. Check value is a label here. Check to see if int is less than 101. If it's not, then we go to the end. We increment, we add 1, and then we output that value. Let's try it. Operand after jump not recognized. Jump 2. Jump 2. Jump 2, check value. Ooh. Wow, you can do this in 2 lines. And you can do this in 200 or fewer steps. My solution is 700. So this is where we start to really change how this is structured. Two lines, dear God. I mean, I don't need this line. Hmm. This is interesting. This is really interesting. Because I could potentially use. I don't know. I know I can reduce this a little bit. Let's do output equals int plus plus. Now, normally int plus plus like this would update after the fact. So let's see. I might need to push this to 1. Yep. Push this to 1. Or does it now return? Oh. Well, that's annoying. Well, fine then. Yeah, okay. Let's see what else we can remove. Let's see. Let's try this. Let's get rid of this. Let's do this. Jump if true to check value. And I'm just going to call this increment, actually, because I think that that's better. Okay. We're down to 6 lines. This is significantly better. We're doing better. Number of cycles 499 as well. We got we removed 1 cycle. Look at us. Look at us. What else can we do to optimize here? So int equals 0. I'm convinced that we have to start with this, but I could be wrong. I could be wrong. Increment int equal or int plus plus output equals int check int equals that. That just seems like I'm gonna try something kind of dumb here. Int plus plus output equals int, and just comment out everything else. Because it loops. It starts at 0. Hey, let's go! Okay, so let me just explain what happened here. Because I was wondering about this, but I wasn't sure if it would work the way I expected. In real life, don't expect this to work so well with assembly. You can't just assume that your registers are starting blank. That's terrible practice. Absolutely terrible. But in this beautiful, idealized world, everything here starts at its default value. The switch is null, red is 0, int is 0, bool is false, string is blank, car is A. So if I just start with these default values, increment each time, and assign the output, then it'll just keep running 100 times, and it'll do it. So this is all you need, and then boom, you get an optimal solution. And we are at 35 minutes already, so I think that's probably where we'll leave it for today. But if you liked the content, please subscribe to the channel. Check us out on Twitch as well if you want to see me do some other just kind of like for fun kind of gaming. And, check out my website or whatnot if you want to hire me for any kind of real programming stuff. But until next time, I hope you guys have a great rest of your day.